All right, so what I would like to do is recreate Thursday's lesson since the video had some glitches that wouldn't allow it to be uploaded properly. So first thing we did was we were talking about a couple more examples of optimization. This is question number 6 from a homework that's now already been due, but nonetheless, I do want to have this recorded so you can go back for reference. Number 6 from homework number 16. So the idea in this was we wanted to figure out how we can construct a cylinder that has a volume of 2,700 cubic centimeters, but minimize the amount of material required to construct it. So whenever you're looking at these questions, it's usually, if there's a question mark in the statement, it's usually right by that, but typically it's at the end in any case, or you'll see the keywords minimize, maximize, most, least, something like that. In this case, we want to minimize the amount of material required to construct a cylinder that would have a volume of 2,700 cubic centimeters. So the amount of material, geometric construction-wise, is related to the surface area. So surface area, just thinking of a cylinder, we have formulas for that. We have formulas for volume. They all involve the radius and the height. Those are the only two measurements we really need. In terms of this sort of information is what's called a constraint. It's a rule that we need to follow. Like, I could minimize the surface area by making a tiny, like 0.00001 radius, and same for the height, but it would never have a volume that's large enough that way. So we have to follow this rule. We have to make sure that the volume, which would be calculated by area of the base times the height, pi r squared times the height, comes out to be 2,700 cubic centimeters. I'll leave the units off of the formula at this point. But what that means is that although R and H can take on any positive values, they're not independent of one another. If I choose a large R, I can choose a smaller H. If I choose a small r, I'll have to choose a larger H in order to make this true. They're related by specifically this equation. Or how this is maybe easiest to solve, if I give you a value of R, do 2,700 divided by pi r squared, and you'll know the value of H that you need in order to make the volume come out right. So this is true for any value of R. I can get H by doing this. So this sort of take this constraint and solve for one variable is a fairly common theme among optimization questions, because I want to minimize the surface area of this. And I can write an expression for surface area, thinking about geometry for just a minute. In terms of, do I need to know every geometry formula under the sun? No. For homework questions, I expect you can look them up. But for tests, realize that anything like this would be listed like, recall, volume of a cylinder is given by volume equals pi r squared times the height, and define what the letters are. Or that the surface area, well, the surface area would be the area of the two circles that form the top and the bottom. So 2 pi r squareds, two circle areas with radius r, plus the lateral surface area. And lateral surface area, like where the soup can label would go, or tuna can label, doesn't really matter what shape you imagine this to be. If I were to cut it and then lay it out, take it off the can, it would be a long rectangle whose height matches the height of the can. But rectangle-wise, this length here would need to be the length that goes all the way around the circle. So is the circumference. So this length is 2 pi r, or pi times diameter, but I'll just use it in terms of radius so we can not introduce any new variables unnecessarily. And so the area of this rectangle part, length times width, 2 pi r h. Just quick review of where that geometry formula comes from. But again, this would be something that would be listed on a test. as opposed to you needing to know this off the top of your head all of a sudden. So this function here, this surface area, this is the thing that we want to minimize. And why this part comes in here handy is, like I said, well, I could make this as small as possible by picking any old values for R and H, but then it wouldn't satisfy the other requirement, this constraint. So if instead of writing R and H as if they're independent and can be anything, if I replace one with its value in terms of the other, not only do I have something that's more easy to understand, I also get an expression that is a function of one variable. This would only have r's in it. I'll call it s of r. So 2 pi r squared plus 2 pi r times this. And if I simplify that, 2 pi r times 2700 over pi r squared. There's a bit of simplifying you can do that'll make your life a little bit easier, just both in thinking about, well, what on earth sort of function is this? When does it have maximum or minimum values? We're looking for a minimum here. But this surface area as a function of radius is given by 2 pi r squared plus, let me call it 5400 r to the negative 1. One factor of r remains in the denominator. So in terms of, okay, now I have a function, I want to find the minimum value of this, and the only restriction is that r has to be greater than 0. Can't be equal to 0 because we'd never get a volume of 2700. R and H, whenever you're dealing with geometric figures, if your variables are representative of their dimensions, just realize that those have to be positive. Sometimes greater than or equal to 0 is okay, but usually it's just positive, strictly greater than 0. If you want to think about this visually speaking, like think about a graph of this, graph the surface area as a function of the radius with the dependent quantity, the thing we're trying to optimize as the surface area, you can see that when r is small, this is going to make, for a vertical asymptote, when we're near r equals 0, when r is large, this fraction would be something small, 5400 divided by something large. And most of the graph would be due to this. What the graph, if you're thinking visually about this, what it would look like in the first quadrant would be something like, it has extremely high values near 0, it dips down someplace, and then higher values later on. The right-hand side of it tends to look like a parabola as r approaches infinity. The left-hand side, there's a vertical asymptote at 0, and we don't care about other stuff that'd probably be in the third quadrant. Yeah, probably in the third quadrant. But we don't really care about it because r can't be negative anyway. So what we're looking for is, where's this spot? And again, the reason that we want this function with a dependent quantity as the thing that we're trying to maximize or minimize is because the derivative, dependent with respect to independent, surface area with respect to radius, that derivative, s prime of r, is either going to be 0 or undefined at these internal critical values, these places that are the higher low points. There's no endpoints to contend with here, so we're just looking for where is this derivative equal to 0. I can't solve an algebra equation, when is this expression equal to smallest number. That's not a sort of thing you can solve, but I can solve for when something equals 0. And from this form, I can say, all right, s prime of r, pretty easy derivative relative to some other stuff we've dealt with, 4 pi r minus 5400 r to the negative 2, otherwise known as 5400 over r squared. I'll just write it this way, and the reason I'm doing that is because of algebra. I'm going to want to set this equal to 0 and solve, which if I set two things subtracted equal to 0, that's the same as one of them equals the other. I'm just kind of skipping some of the algebra in terms of writing it down. But you can see from this form, oh yeah, multiply both sides by r squared to get rid of this denominator. Normally you don't multiply by a variable, but as long as I know that that variable is non-zero, it's legal. So I get 4 pi r squared, or r cubed rather, is 5,400. And so to solve for when r equals 0, there's exactly one answer. Divide and take a cube root. 5,400 over 4 pi, the cube root of that, would be the precise answer. You can round that to a decimal if you're asked for something like approximately what would the radius need to be. If the question actually asked for what is the minimum surface area, realize that this is not the answer to what's the minimum surface area. This is the answer to what radius will minimize the surface area, or minimize the amount of material needed. If I wanted to know what is that amount of material, I just need to substitute in that value of radius in both those spots, either in its exact form to get an exact value, or more likely than not, a decimal value would be something appropriate here, because thinking about if you were physically constructing these and you needed to purchase the material, you're not going to be able to get quantities measured in radical form. In any case, again, our strategy is figure out what it is that needs to be done, draw a diagram, write out some facts you know, come up with some formulas that relate to those if it's something geometric. But overall, in order to minimize a specific quantity, you need to write a function whose dependent quantity is the thing that you're trying to maximize or minimize, so that you can use this trick of derivative equaling 0, or in uglier cases, undefined, when it's something like a low point, something like that. Keep in mind your domain, just in case something is out of the domain. By the time you find a critical value, like if this had a critical value at x equal or r equals -7, we wouldn't care about that because it has to be positive only. All right, so let me clear off that one. Another question I want to take a look at is, let's see, from homework 17. Question number 6 had the most requests to be done. And this is one where we had, let's see. What were we looking at here? Oh, we had a right triangle, and we wanted to know something about what gets, let's see. All right, so sorry, I forgot what the question was. I had the wrong page up. So this one was about a fence needing to reach over a ladder reaching over a fence to reach a house on the other side. So there's not a picture in this diagram, and it's not a standard geometric figure, but the idea is there's a house. We'll assume that the house's wall stands vertical. There's a fence that is 6 feet away from it and is 3 feet tall. Doesn't really matter how tall the house is. We're not specifically trying to reach the corner of the roof of the house or anything. Just we need to figure out what's the shortest ladder we can use to reach over the fence and hit the wall of the house. So, for instance, between the fence and the house, wherever we draw it, it would have to reach it'd have to hit the top of the fence and go to the house from there. And since it's assuming a straight ladder, pretend that's a straight line, it would reach the ground someplace out farther. I want to know what's the length of this fence. Now, I just picked a random angle here. You can see, though, if I picked a lower angle, this would reach out even farther that way. That would be a longer fence. Or if I made a steeper angle, it would maybe be shorter. But if I do it too steep, it's going to have to go way up the house, although it won't have to go very far into the yard on the other side of the fence. So the idea is to minimize the length of the fence. So this diagonal length here, where I know this height is 3, this distance is 6, and that's all I have to deal with. Like, this can be as tall as I want, this can go out as far as I want, but realistically speaking, I don't want this to have to be too tall because I want a relatively short ladder. So there are, in this triangle that I just constructed by drawing the rest of it, there's a lot of potential little sub-triangles, but let me just think about the overall picture. End of the ladder along the ground, I'll call that X. End of the ladder up the wall, that length, I'll call that Y. Just vertical Y, horizontal X. So that the length of the ladder is something that now I can describe in terms of X and Y, right? So the length of the ladder, I'll just call it capital L, would be the square root of x squared plus y squared, right? That's not too bad. And I want to minimize L. Now, there's not any other formula that was given, like the ladder has to be at least something number of feet long, but I know just from this and the fact that x and y are, again, geometric measurements, that x and y so far have to be greater than 0. L is also going to be something that's greater than 0, but that'll happen naturally because I don't have a plus or minus in front of my radical sign, just regular square root. So one thing I want to point out here, this is a trick that's used in many questions where it involves a distance, this like distance formula, Pythagorean theorem situation. Since this stuff underneath is two positive quantities added, there's no like negatives, nothing canceling out here. If I'm trying to minimize their square root, that means I'm trying to take the square root of the smallest thing possible. So in reality, if I minimize just x squared plus y squared, and don't worry about taking the square root of that, although it's not the length of the fence anymore, I'll call it, or the length of the ladder anymore, I'll call this s for squared version. If I minimize x squared plus y squared, then L, the length of the ladder, given by this formula, would also be at a minimum, right? Because if I make the smallest possible positive number here, this is definitely going to be something positive, then when I take its square root, it'll be as small as possible still. Reason I'm just going to do that is to simplify the derivative. Now, I do have to somehow relate x and y. I do have to somehow incorporate the fact that the fence is 3 feet tall and is 6 feet away from the house. And how we're going to do that is utilizing some similar triangles. I think we talked about similar triangles at the end of the last class, but in this triangle here, from the point on the ground to this right angle, up to this corner that meets on the house, I can see that's a right triangle. I also have a smaller right triangle, let me change colors, that shares the exact same corner angle where the ladder meets the ground, and also a right triangle, so this has to be similar to the overall triangle, right? They've got the same 3 angles, so it's the same ratio of side lengths. So thinking about that, well, this is something else that we also did, I think when we were talking about the laying cable across the river for Cox Communications or something. If this whole length is x, and this length, which is not part of a triangle, at least not right now, is 6, then this length right here I can express as x minus 6, right? X minus 6 and 6 are going to add up to x. So this length 3 corresponds to that side y. This length x in the large triangle corresponds to x minus 6 in the small triangle. And using those kind of together, we can come up with an expression for y in terms of x, because that's what we need. What we really need here is to have not 2 separate variables, but to have y in terms of x or x in terms of y. And it doesn't matter which, but let's go back to this proportional relations here. So let's see, the bottom side of the small triangle corresponds to the bottom side of the big triangle, in the same way that this vertical side in the small triangle corresponds to the vertical side in the large triangle. So here's a proportion. I should easily be able to get y by itself. Just, cross multiply if you want, or just think about multiplying certain pieces around. But like, you can flip-flop things on diagonals or all sorts of shortcut rules, but this is just algebra. Let me write out a little bit. Y times x minus 6 would equal 3x. So y is going to be 3x over x minus 6. So now I have y written in terms of its relationship to x, which means I can write s instead of this squared version here, instead of being a formula involving x and y, I can write it with just x's. So I'll call it s as a function of x is x squared plus 3x over x minus 6 instead of writing the symbol y squared. And from here, now we've got our objective function, the thing that we're trying to, in this case, minimize. If I minimize the square of the length of the ladder, then I take the square root and I get the length of the ladder that's the shortest possible. So the algebra isn't, super nice in terms of solving this, but I can certainly take a derivative. The only thing I have to worry about with x is that, well, I know from this that x is greater than 6, right? So x is 6 plus some extra. So I'll say x is greater than 6 as the restriction of my variable. But s prime would be 2x plus the derivative of this, which you can either square out that fraction or you can use chain rule. I'm just going to use chain rule. 2 times the fraction to the first power times quotient rule, the derivative of that fraction. Numerator's derivative times the original denominator minus other way around. Denominator's derivative, which is 1, times the original numerator, all over the denominator squared. So cleaning up this derivative just so we can think about how would I figure out when that's 0 or undefined. Let's see, here's a nice easy term. This quotient rule part, if you notice, I can change colors here, I'd have a 3x minus 3x, so those are gone. All I'm going to have left is 3 times negative 6 in the numerator, or negative 18. It's multiplied by another fraction where I'd have, let's see, 6x times negative 18. I'm just going to write that. 6x times negative 18. Don't know what 18 times 6 is off the top of my head. All over x minus 6 times x minus 6 squared. So in terms of solving for when is this undefined or 0, it'd certainly be undefined if x was 6, but if x was 6, that would be the ladder going straight up into the air. That's certainly not going to minimize this. So if I want to know when this is equal to 0, it's going to be a mess. Let me just show this on GC. So what I want to know is there's two things you can do. You can, if you're looking at this like, oh, that algebra is unpleasant, you can graph the derivative and see when it's equal to 0, or you could graph the original and see where its minimum is. And those should be the same, in this case, x value. Like I say, it's not an awful expression, but it's just not super pleasant. I'd have to be solving, let's see, 2x equals, let's see, 18 times 6 is the same as 9 times 12. 108? No. 8 times 6, yeah, 108. So you can maybe see, if you're solving this, you're going to have to expand that x minus 6 to the third power. You're dealing with this, or actually you don't need to. You could multiply it across and then divide. Since x can't be 0 anyway, do the same trick as last time. 2x times x minus 6 cubed equals 108x. Divide both sides by 2x. And we get x minus 6 cubed equals 54. So to get x, I'm going to take a cube root and then add 6 to both sides. So it's a cube root of 54 plus 6. So don't know what the cube root of 54 is off the top of my head. Somewhere between 3 and 4. But that means the x value, not the length of the ladder, x is how far the bottom of the ladder is from the bottom of the house, I guess. But this is the value of x that helps us reach our goal. Once you find that, you can plug it back in here to see what the length of the ladder is. I mean, you could plug it in here if you wanted to see what the length of the square of the length of the ladder is. But in any case, if you just want to know x and y separately, Here's how you can get y once you know what x's value is, and so forth. But this is actually a minimum, not a maximum. This function here, in terms of what it looks like, has a vertical asymptote at 6, but we're only concerned about what's to the right of 6. And to the right of 6, it decreases, then increases again. So we're looking for this, it decreases up through this value, like 9 or 10 or something. And then it increases after that. All right, so we'll do something else on GC. But let's get back to the pond obstacle question that I brought up at the end of Tuesday's lesson. Clear this all off, maybe. All right, so this pond obstacle, the situation was, it's like one of those Spartan races where this is in the middle of it. Let me shrink this a little bit so you can see some of the text. And I posted this example so you can read the whole thing on your own size, but there's this pond with a radius of 1.8 kilometers. The racers are coming up from one side of it. They have to go past it somehow. They could swim straight across, they could run around the edge, or they could do a combination of those two. And what we talked about last time was that for Erin, since she knows on this rocky terrain around the edge, it's hard to run on, slippery, so you don't really want to swim first. She can run on it at 4 kilometers per hour, or she can swim through this pond at 3 kilometers per hour. So if we want to know what's the ideal route for her to take, that's essentially figuring out, well, where is this point where she stops running around and then starts swimming? And it could be all the way at the beginning. She could just not run and swim straight across. It could be that it's all the way over here, as in she doesn't swim at all, she just runs all the way around. Or it could be somewhere in between. And in terms of modeling this position, we could do it by XY coordinates, but thinking about, since this is a circle and it just increases in distance from the beginning smoothly as I allow a central angle theta for this circle to increase. I can say also, based on the trig we were talking about last time, that if I define this angle, this central angle in the pond, to be theta, then the length here demonstrated would be theta times the radius, so 1.8 theta kilometers. That would be how far she'd run in this diagram. Figuring out how far she swims is a little bit more challenging because although this is just an arc length, and as long as theta is measured in radians, then a measurement of theta radians is theta radius lengths around the edge of the circle in terms of the arc that it creates. This is a secant line through the middle of a circle, but not through the center, just through a circle through 2 points. So in terms of figuring out this length here, I need that to be something that I have a formula for. I don't have any formulas for how do you find like if I have this line here, how do I find the length of a line that I randomly draw through a circle? There's not a formula for that. But if I relate it to triangles, so there's a non-right triangle already drawn here. That's not particularly helpful because I don't know any of its angles. But I can draw a right triangle that includes this angle theta and will also help me around. Now, this large red triangle doesn't have this angle theta, but one of the sides of this large red triangle is in a triangle with angle theta. And therefore, based on trigonometry, I know that the length of this portion of that side and this vertical component here can be described in terms of trig functions of theta. This vertical, opposite from angle theta, would be scaled up by a factor of 1.8 like everything else, 1.8 kilometers, times the sine of angle theta. And this horizontal component is 1.8 times the cosine of theta in terms of number of kilometers. And this length, the rest of this bottom side here, well, that's from the center to the edge. So that's the radius, 1.8 kilometers. So although I don't yet have the hypotenuse of this triangle, I have all the ingredients now to find it. a squared plus b squared equals c squared. So this length that she's going to swim would be, let's see, this is the easiest one to write, 1.8 sine of theta squared plus this other length would be 1.8 plus 1.8 cosine theta. So that's the a squared plus b squared. I don't really want to know c squared. I want to know c. So I'll take the square root for now. We'll see if we can do the same trick as last time. But this would be the length that the distance that she swims for any angle theta, where we're taking theta to be between, in this picture, 0 to pi. It would obviously repeat if I were to go pi to 2 pi radius lengths. So 0 through pi is my domain for angle theta. So we still don't have written, though, altogether. We talked about this a little bit on Tuesday, but what we're actually trying to do, get past the obstacle as quickly as possible. As quickly as possible means we want to minimize time. So these are distances. We certainly want distances to be small to minimize time, but she's going at different speeds. So just thinking distance equals rate times time, if I convert that around, time would be equal to distance divided by rate. And we have all the distances. We have the rates. So we should be able to write expressions for time. The total time it takes her to pass the obstacle, we can write as a function of theta, but it'll be based on knowing her time that she's running plus the time that she's swimming. And what we have up above are the distances for each of those. Here's the distance running and the distance swimming. But here's the rate of running and the rate of swimming. So it's just an additional step from there. I'm going to write this in a different color. The time it takes her to pass the obstacle when the angle is theta is given by, let's see, time she's running would be distance running over rate at running. So 1.8 theta over 4. And that could be reduced, obviously, but let's just write 1.8 theta over 4. Plus, for swimming, well, it's going to be this distance over 3. I'm just going to write a star here. It's that whole hypotenuse formula divided by 3. So, as long as we keep theta in the interval 0 through pi, sorry, this little symbol here means in the interval or is an element of. So as long as theta is in this interval here, 0 to pi, then we should have all the possible values of time that it takes her to complete this. Now, considering that this is the numerator, and I can't just square everything because, well, this is a sum of two terms. I could, but it would create like a FOIL, distributive property situation. So it would not make our life easier. And as it is, it's pretty unpleasant. And although we could find the derivative, what I want to show you is what I was talking about last time. Let's say that she's trying to estimate this, right? This is for her own purposes. She doesn't need to construct something to exact specifications for a spaceship or something. She's just trying to win a race. So let's say we can estimate this in terms of decimals. Let's look at the graph of this objective function on the interval 0 to pi and see where it has its minimum. So I typed this up earlier because it's kind of a pain to type. But here we go. T as a function of theta, 1.8 theta over 4, distance, or time running rather, plus the time swimming, a squared plus b squared under square root, and then divided by 3, her speed in kilometers per hour for swimming. And then what I want to do is, oh, by the way, this theta symbol, just like pi, if you type out theta, ooh, it it turns into a symbol by the time you finish it. So theta is just spelled Theta in English, and when you hit the A, it turns it into that symbol. But what I want to do is graph y equals capital T of x. And I want to graph it from 0 to pi. So to graph this, here's our 0 to pi. Doesn't extend very far. We can zoom in if we want. I can see that over that interval, the time starts here, increases, and then decreases again. Now we're looking for a minimum value of time. So I'm not looking for, like, if I went through, take the derivative of this and set it equal to 0, I would have gotten this spot, which is a maximum and not what I was looking for. I'm looking for a minimum. But on this interval, the minimum, as you can see, occurs at one of the endpoints. And if you look closely enough, you can see, just visually speaking, it's at this left endpoint here. This is at 1.2 versus the right endpoint is at, looks like about 1.4. So this at 0, meaning, back to this picture here, at an angle of 0, meaning don't bother running, just jump in when the angle is 0 and swim straight across. That's your fastest way across. Now, it doesn't tell us the time. We'd have to sub back in to get that. But the lowest amount of time that it takes is at time 0. Now, however, that function, since I have it in GC, I can evaluate t of 0. You can probably even do this manually. Sine of 0 is 0, cosine of 0 is 1. So it's not maybe too hard to work that out manually, but since I have this already plugged in, t of 0, you can see it is exactly 1.2. Not just approximate because it looks like it in the picture, but that's nice succinct value. And I do have my document settings to show, let's see, to show 8 significant digits. So this isn't just rounded off from my document settings. T of 0 is exactly 1.2, or it takes 1.2 hours for her to get past the pond, and she does that by not bothering running, just swim straight across. Because although she runs faster, it's not faster enough to make up for the fact that she should have to run so much farther. All right. So that's the end of our optimization and trig review sorts of topics. What I want to jump into now is what's called implicit differentiation, which we'll use for a different sort of derivative application, and we'll also use to be able to find derivatives of some other types of functions that we didn't do on the mastery test. So let me open up Keynote. That looks kind of frightening, actually. Actually, do I have another? Yeah, let's just take a look at this here. This is on the Keynote that I'm going to open up for you. But take a look at this relationship here. I won't call it a function because this is clearly x squared plus y cubed minus 2xy equals 7. It's a relationship between x and y, but looking at what that means, this is a picture of all the xy pairs that make this equation true. But you can see that it doesn't fit the definition for y being a function of x, nor x being a function of y, because, well, this left-hand side is all fine, but when we get up to around x equals 2, 3, 4, there are several different y values that correspond to the same x values in this region here. So giving a single value of x doesn't give one specific output, it gives a variety of solutions. But nonetheless, thinking about graphs and derivatives, I can see that this function, as I go from left to right, in this area here, where it's clearly a function, well, those derivative values would be something positive, y with respect to x. Derivative of something positive here, y with respect to x. Now, when I'm describing this area, it's kind of weird, because it's not like as you go from left to right, because as you can see, I go from left to right and then right to left. And so just thinking about in a neighborhood around this point, if I'm thinking of a tangent line, I know that right around here, this graph is fairly flat. So I think that this relationship here should have a derivative value near 0 if we're around the point, like this is like approximately 2, 2. So 2.3 and 2.3. So if we're around this area, I think that the derivative is pretty close to 0, change in y with respect to change in x. Now, if I just go a little bit farther over here, say, well, if I'm thinking about this region, when x is almost 4 and y is almost 2, I can say, well, left to right, if I make a tiny change in x and a tiny change in y, this goes downhill from left to right. So that would mean that I should have a negative derivative here. Now, if I go around this corner here, approximately same x value as before, but a different y value, I can see from left to right, this graph is going uphill. Like if I were to imagine, like zoom in and look what's going on inside that little blue square, the graph is going uphill from left to right. So I should have positive derivatives, change in y with respect to x here. And then negative derivatives, again, around the same x value. So when x is around 3, I've got 3 different solutions, 3 different xy coordinate pairs on this graph. And at each of those, I can describe what's going on with the function. At the top one, I've got a negative rate of change. In the middle one, I've got a positive rate of change. And at the bottom one, I've got a negative rate of change, meaning left to right, right in the immediate area of where this vertical line is crossing the graph. Moving left to right, x is decreasing a little tiny bit here. It's pretty close to 0, but decreasing a little here, increasing a little here as I go from left to right, and the y value is decreasing a little bit here. So we should be able to come up with a formula for a function rule for some sort of expression that tells us about the derivative of this, even though I don't have it written as a function. I don't have y equals and then only stuff with x. And in fact, we don't even have to solve this to get y equals and put it in pseudo function form, despite the fact we know it's not actually a function. So even if we could, it would be a mess. But I don't have to have y equals to find dy dx. So here's what I mean by that. Think about functions that things that certainly are functions. Like if I have, let's see, y equals 2x plus 5. All right, so simplest sort of derivative you can take. I could say that dy dx is 2. Now, if I had this rearranged and it said y minus 2x equals 5, without moving this around at the beginning, I can still find the same result. And here's how I can do that. I can take a derivative of each term. So think about like algebra style. Instead of just thinking, oh, I'm taking the derivative, so I'll name it the derivative, and then I'm just doing the derivative over here. Think about this as an algebra equation. Take the derivative with respect to x of both sides of this equation. So the right-hand side, I think, okay, the derivative of 5. That's easy, that's 0. The derivative over here, I've got 2 terms, so it's a sum or difference rule. Just take the derivative of each term separately. So the derivative of y with respect to x, not the derivative of x with respect to x, the derivative of y with respect to x. That's literally the symbol dy dx. That's what that symbol means, the derivative of y with respect to x. And then just like with sum or differences, you can just write down a negative sign and take the derivative of what's after, or imagine this as a plus and put a negative sign on this. But the derivative of negative 2x is negative 2, when I'm taking derivatives with respect to x. And if you can see what we have here, we have an expression that's algebraically equivalent to this. So if your goal is, find dy dx, well, from this point, after doing the calculus, it's a one-step basic algebra 1 equation, just add 2 to both sides. So if dy dx minus 2 is 0, then dy dx is 2. And although we did move things across, we didn't do it in the original, only in the derivative. So let's do the same with this. This one's significantly more challenging derivative-wise, so there'll be a little bit messier algebra at the end. But think about this, we're going to think about the same strategy. Thinking about not worrying about getting y by itself to start with, but just imagine taking the derivative of both sides of this equation. We'll get some expressions that have dy dx in them as a result of that. So let me pull up the keynote for this so it's typed and not quite as messy as my handwriting. All right, so here's that same function, just zoomed in a little bit closer. X squared plus y cubed minus 2xy equals 7. And what I said about this was, this is a representation of that equation because they both represent the same set of ordered pairs, xy, that make the equation true and are points on the curve. So like the xy pairs that make this equation true are the same set of xy pairs that are demonstrated visually here. So we already talked about this. Does it represent y as a function of x? No. That whole vertical line test, if you want to think about it, or knowing an x value does not uniquely determine a y value. Meaning knowing an x, I don't necessarily know what y value you're talking about because there are multiple y values in certain areas of this function. But we should be able to talk about how y changes with respect to x because that happens not over like several units at a time, but over extremely small differential sized intervals. So at any point, y is changing at some specific rate with respect to x. We just have to make sure we're only looking at a very small neighborhood around a given xy point. Meaning, if I have not just an x value, but an xy pair, I can specify what the rate is. So just like we were talking about before, if I said, oh, x is 2.2 or something, like, well, you have to tell me not just what the x value is, but also which y value you're talking about to nail down one specific point on the curve. But if you're given a full xy pair, then you will be able to find, if we do that implicit differentiation, differentiate without having to get y by itself first, we can get a formula that involves x and y both, and in the case of something that's not a function, and be able to find a value for that derivative. So in order to determine dy dx, the change in y with respect to the change in x, or the derivative of y with respect to x, we kind of pretend that y is a function. If you want to write it out this way, you can, instead of writing the symbol y, you can write f of x, like pretend it's a function. Or you can just do what we did last time. Oh, taking the derivative of y is dy dx. So we're implying that y is some function when it's jumbled into the middle, but it doesn't really matter whether it is or isn't. So this is called implicit differentiation, or something like this is an implicit xy relationship, meaning it's not solved for one in terms of the other explicitly. It just relates the two of them to one another implicitly. So what I mean by this, pretend that y equals f of x. So in the case that we just went over with the linear function, it was easy enough because y only appeared once and it was only just its own term, y. Here we've got y show up a couple of times. It's not nearly as easy, but the same thing is going to hold. We want to think of, if you want to, you don't have to replace y with f of x. This is just a suggestion that's made in your text in terms of keeping things straight. You can think of replace the y with the x and then take the derivative of both sides of this equation. So let me write out the steps from here, because this gets a little bit messy. But doing what you did before, the derivative of 7 with respect to x, just like the 5 we had in the last example, is 0. In this side, we have 3 terms. The first one's derivative is easy. What's the derivative of x squared with respect to x? Oh, it's 2x. Next, what's the derivative of, well, it's not just f of x, or it's not just y. It's f of x to the third power. Well, if it was a whole formula written out like 5x squared plus 9x plus 2 cubed, you know we'd use chain rule. Same thing here. What's the derivative of something cubed? It's 3 times that something to the second power. And then chain rule times the derivative of what's inside. Well, I can write that as f prime of x or dy dx. But I've got one more term to deal with here, and this one's a little messy. This one involved chain rule. I've got to take the derivative of 2x times f of x, or 2x times y. It's a product. X, I know that the derivative of 2x is 2. F of x, the derivative on its own would be f prime. But if I have a product of the two, this requires product rule. So I'm going to scoot this equals 0 to another line. But I take the derivative of the 2x times the original f of x plus the original 2x times the derivative of f of x. And then there's that equals 0. So here's our product rule. It's easy to forget that this is the product because it just looks like, oh, it's 2xy. But realize if you're starting to take the derivative of things that are jumbled together, like you know how to take the derivative of 2x, you know how to take the derivative of y, it's y prime or f prime of x or dy over dx, but those are multiplied together. So you have to use product rule. Now, at this point, we've done all the calculus that's required, but note this isn't solved for dy dx yet. If we want to find dy dx or find f prime of x, now I wrote f prime of x because that's what we've got written in here, but in the original problem there was no f of x, we made that up. So find dy dx, so f prime of x, not f of x, but f prime of x is the same as dy dx. Notice that it's multiplied on here, and it's multiplied on there. There's 2 terms in this expression on the left-hand side that have f prime of x or dy dx in them. There's also 2 terms that don't. So just in terms of algebra stuff, regardless of what sort of equation you have, if you are trying to solve for a given variable and some of the terms contain that variable and others don't, you separate them in terms of put some on one side of the equation and the others on the other. So that's what we're going to do here. I'll just leave these messy terms with the f prime on the left-hand side of the equation and subtract this, and we'll add this since it's after a subtraction sign to put them on the right-hand side, so that we can solve for our variable, solve for the expression that we're looking for. So f prime of x is going to be in the 2 terms that are on the left-hand side. It's multiplied onto, I'm going to factor as we go here, 3 f of x squared. And then this other term is minus 2x f prime of x. So if I factor out the f prime of x, I get minus 2x. So moving this and that, the terms that didn't have f prime, over to the other side, I'm going to have negative 2x and positive 2f of x. And so to solve for f prime of x, otherwise known as dy dx, it's just divide. To get this by itself, I'm going to divide by this quantity in parentheses. So f prime of x is going to equal a lovely fraction, negative 2x plus 2f of x over this stuff, 3f of x squared minus 2x. Oh, sorry, I have too many sets of parentheses here. don't need that one, it's in the denominator. So again, f of x was something we constructed. You don't have to go through this process of putting in f of x instead of y, but if that helps you keep straight the fact that y is considered to be the output, the numerator part of the derivative, and x is considered to be the input, then please go ahead and do that. But realize that translating this back into just x's and y's, this would be the same as dy over dx equals negative 2x plus 2y. Instead of having f of x, I have y. And in the denominator, 3y squared minus 2x. So you can see that substituting in an xy pair will give me a value for this derivative. So looking at a place like, I'm just eyeballing it now, not actually on GC. Let's say that this point is about 2 point, let me just call it 2. Looks like about 2, 2. Just to use numbers that I can do manually. So if I were to substitute in 2 for x and 2 for y, you can see from this numerator, it's going to be 0. The derivative value is going to be negative 4 plus 4 over something. But at 2, 2, that derivative value would be 0. And this is just an estimate of what this point is, but that makes sense relative to the relationship between x and y here. If I were to pick a point like this, which seems to be about, let's see, I'll have to be a little bit more accurate here, 2.2 and negative 0.5 or something. I think it's 2 1/4 and negative 1/2. I would expect, based on the shape of this, and again, just look at this small region as if the rest of the graph doesn't exist. From left to right, this is going uphill. So I'd expect a positive derivative value when x is a little bigger than 2 and y is about negative 1/2. And if I look at this value here, 2.25, I don't know why it's not writing this, negative 0.5, I'd have a numerator expression. Let's see what, negative 4.5 plus negative 1, so negative 5.5 as my numerator, and in the denominator 3y squared, 3 times 0.25 sounds like 0.75 minus 2x. So let's see, minus 4.5. So this is a negative over a negative, negative 5.5 over negative, what is that, 3.75? So some sort of positive, not an extremely large number, but a slightly positive number, which is good because that's what the graph looks like, positive slope in that region right there. So in any case, these derivatives have the same meaning in terms of graphs of functions or of non-functions where two variables are involved and one is not a function of the other. The derivatives still have the same meaning in terms of the graph of the relationship that does exist between them. It's just trickier to imagine because you can't talk about intervals of x and what happens over them because as x increases, sometimes you get multiple y values. So I can't talk about as x increases from 0 to 5, I can trace the graph, but y goes up and then y goes down, but x is going backwards, and it's a bit more complex a relationship than just to describe from left to right what's going on. All right, so we'll do some more examples of just straight implicit differentiation as a part of why we want to deal with that in the first place. So suppose that I have a figure, a cube, where the edges of this cube are getting longer and longer. So it started out as a small cube, and then the edges are getting longer at a rate of 2 centimeters every second. So it's constantly increasing in terms of the lengths of the sides. We want to know how fast the volume is changing at some point in time later. Now, if you can imagine thinking about taking a small cube, just going to go, yeah, taking a small cube and increasing the sides by a couple of centimeters, that's going to increase, and I'm not a great artist, that's going to increase the volume by a little bit. It's like putting a coat of like in 1 second, this is going to be 2 centimeters thicker all the way around in each of 3 dimensions. So it's going to be bigger, it's going to be taller, it's going to be wider. It's still going to be a cube, but it's kind of like we just coated this cube with a 2 centimeter thick layer of paint. And so its volume got larger by the amount of paint, the volume of paint that we added to it. Now, if I'd had a larger cube to start with, now excuse my cube drawing here, if I think you would agree, to get a 2 centimeter thick coat of paint on something that's this large, it takes more paint than it does to get 2 centimeters thick on this. So it's a larger increase in volume when my cube is larger than it is when my cube is smaller, even though I'm adding the same amount every second in terms of how much larger the edges are getting, if you want to think of it that way. So although the edge length is increasing at the same rate all the time, the volume is going to be increasing more and more quickly because, like, relative to time, but also relative to the number of centimeters of edge length that we've added on. But what we're looking for here and what this little diagram is, I know how edge length and volume are related. That's a geometry thing. So volume of a cube is, I'm just going to call it x for edge length instead of using e or s or something else. So if I have a cube whose edge length is x, it'd be x by x by x. This is how the volume and the edge length of our cube are related. But what this is describing is that in reality, x is changing, not just on its own, but over time. As time increases, x keeps getting bigger and bigger. So I could write a formula for x and how big it is if I knew like how large it started and what time we're at. But let me just write x is a function of t. X is a function of time. I'm using, your book does this also, but t is just used in a lot of cases like this for some sort of generic time. So in this case, it'd be seconds. So this x of t, we're not going to fully define this t, but just say, well, x depends on time. Volume then also depends on time, right? But whatever the output to this is, if the input is some amount of time in seconds and the output gives me what the edge length is, once I know that edge length, I cube it and I get volume, which would by default then also be based on time. So at any one point in time, I get this kind of like a composition of functions. At any point in time, I can construct an edge length, and then from that edge length, I can get a volume. So volume depends on time in that sense. Now, the lucky thing is we don't actually have to write out what is the relationship between x and t. We just have to know that this, the rate at which the edge length changes over time, this is a rate of change. So the rate of change of the edge length with respect to time is 2, according to the problem, 2 centimeters per second. So x is the edge length measured in centimeters. The rate of change of the edge length over time is 2, and that's measured in centimeters per second. So t is this mystery, oh yeah, it's just in seconds. So you see this dx dt or x prime of t or something like that, where it's just, we're looking for a rate per second in this case. Notice that this asks, how fast is the volume changing? The question's asking us to find the change in the volume with respect to time. And we're using V to represent the volume. in cubic centimeters. So this, how the volume changes over time, just using the units from the problem, would be cubic centimeters per second. But in any case, this here, quantities equation, we know how x and v are related, right? V equals x cubed. Simple, right? What we want to know, if one changes with respect to something else, in this case time, how does the other change? Well, you can think of it like, just like the last question we're doing with, you can put in this function notation if you want, or you can leave it alone as it was. But what I want to do is find the rate of change of v with respect to t, v prime of t or dv dt, at a specific point. So this, when the length of each edge is 50 centimeters. That's apparently going to be important in our future because, like I said, the volume changes at different rates depending on how big or small the cube is. So I'm just going to go with the basic v equals x cubed. I know dx dt, I'm trying to find dv dt. How I'm going to get dv dt is by taking this, notice there's no t involved here, and taking a derivative of both sides with respect to time. So if I take a derivative of v with respect to t, that's called literally dv over dt. If I take a derivative of x cubed with respect to t, notice x is not t. Those are two different things. This is like what we were just doing in the previous problem when we had that y cubed and we're taking a derivative with respect to x. This involves chain rule. X is a function of time, or x varies over time. I don't know what the formula is and I don't really care. I just know that x is related to t. So the derivative of something cubed is 3 times that something to the second power, and then chain rule. What's the derivative of x, the inner part, with respect to t? Dx dt. Just the same way. So the derivative of v with respect to t is dv dt. The derivative of x with respect to t is dx dt. The derivative of functions of those involves chain rule. That's where this 3x squared comes from. This 3x squared times dx dt, that's taking the derivative of this something cubed with respect to something else. So derivative of x cubed with respect to t, derivative of y cubed with respect to x, derivative of, whatever it might be. If this letter and that letter don't match, we get to do chain rule. So in any case here, what we have, we started with a formula that related v and x. If I give you any side length, you can give me the volume. Or if I give you the volume, you can give me the side length. What we have now is a new relationship that involves 3 things. How fast the volume's changing, how fast the side length is changing, and a third thing, the actual current length of the side edge. So it involves knowing 3 things. Luckily, our question asks, how fast is the volume changing? This is the one we're supposed to be finding. And then it gives us the other 2. When the length of each edge is 50, and dx dt is this 2, how fast the edge length is changing. So dv over dt, the rate of change of the volume at this particular point in time when we evaluated this, is 3 times 50 squared times 2. So what, 6 times 2,500? 15,000, I think. That's the number part of it. If you want to put in the units into the formula too, this is 2 centimeters per second. This is 50 centimeters that gets squared. So I'd have centimeters squared times centimeters per second. This makes centimeters cubed per second. But that's also what we said would make sense for a change in volume with respect to time. All right, so that's one example of this. We'll go through several more examples on Tuesday of applications of this, and I think I listed them out already. We'll talk about what if it's not a cube, what if it's a sphere, it's a spherical balloon that's being inflated, or what if it's not just a nice symmetric geometric shape that's getting larger or smaller, but just some other motion that occurs over time at a regular rate. How can I relate this? The trick to all of this is starting with a relationship between the general measurable quantities that we're dealing with, and then take a derivative with respect to something else, time, usually speaking. Take a derivative with respect to time, which involves some chain rule, implicit differentiation, or implicitly imagining that x is a function of time without writing out what is the relationship between x and t. We don't have to know that to answer this question, as you noticed. So write a relationship for the general quantities, differentiate it with respect to time most of the time, and then have a new equation that relates different things. It has these derivatives that are in the relationship. All right, that's it for today. Thank you.